The bugs framework aims to address all these CWE and CVE problems. It has the expressiveness power to clearly describe any software bug or weakness underlying any vulnerability. To solve the problem of imprecise descriptions and unclear causality, BF is being developed as a structured classification. The BF description of a vulnerability provides causal relationships, forming a chain of underlying weaknesses leading to a failure. To avoid gaps and overlaps, BF is being developed as a complete orthogonal classification. BF describes a weakness as an improper state and its transition. The transition is to another weakness or to a failure. An improper state is defined by a tuple, operation and its operands, where at least one element is improper. The initial state, depicted in blue, is always caused by a bug, a coding or specification error, which, if fixed, will resolve the vulnerability. An intermediate state, in light purple, is caused by at least one improper operand. The final state, in dark purple, ends with a final error, which causes the failure, undefined or exploitable system behavior. A transition is the result of the operation over the operands. For example, here, operation 1 from improper state 1 is improper due to a bug and results in improper operand 2i, leading to improper state 2. The last operation results in a final error, leading to a failure. BF describes a vulnerability as a chain of improper states and their transitions. Each improper state is an instance of a BF class. The transition from the initial state is by proper operation, an operation that has a bug, over proper operands. The transitions from intermediate states are by proper operations with at least one improper operand. The operand is at fault. The improper operation or improper operand is the cause for that weakness. The improper result from an operation over its operands is the consequence from that weakness, and it becomes a cause for a next weakness or a failure. Knowing the failure and all the transitions at execution, we should be able to find the bug. Simply go backwards by operand until an operation is improper. Fixing the bug within that operation will resolve the vulnerability. In some cases, several vulnerabilities must be present for an exploit to be harmful. The final errors resulting from different chains converge to cause the failure. The bug in at least one of the chains must be fixed to avoid that failure. BF's approach is different from the CWE's exhaustive list approach. BF is a classification system. Each BF class is a taxonomic category of a weakness type. It relates to a distinct phase of software execution, the operations specific for that phase, and the operands required as input to those operations. Operations or operands improperness define the causes. A consequence is the result of the operation over the operands. It becomes the cause for next weakness or is a final error leading to a failure. The attributes describe the operations and the operands. They help us understand the severity of the bug or the weakness. The BF descriptions of a weakness is an instance of a taxonomic BF class with one operation, one cause, one consequence, and their attributes. Any vulnerability then can be described as a chain of such instances, and their consequence calls transitions. The BF taxonomy consists of clusters of bugs classes with valid cause operation consequence relations and attributes. We have developed BF bugs models to help us identify the clusters of BF classes. They show the phases where particular types of bugs could occur and the possible flow of operations. Each model assures the phases and their corresponding BF classes do not overlap in operations. The models help us also understand how security could break. Once formalized, they'll help us define secure coding principles such as input-output safety, data type safety, and memory safety. For example, the data type bugs model shows the identified phases, operations, and flow for declaration, name resolution, type conversion, and type computation bugs. Each data type weakness involves one data type-related not overlapping operation: declare, define, refer, call, cast, coerce, calculate, or evaluate. Each of these operations is over an entity, object, function, data type, or a namespace. A declared and defined entity is referred in source code via its name. Names referred to in remote scopes get resolved by resolved namespaces. Resolved data types get bound to objects, functions, or generic data types according to their declarations. Resolved functions get called. A resolved and bound object may be converted to another data type and used in computations as an argument or as a return of a called function or to call a member function. A passed-in argument is expected to be of the declared parameter data type, and the passed-out result is expected to be of the return data type. Otherwise, casting explicit conversion is expected before the call, or the value will be coerced, implicitly converted, to the perimeter data type or the return data type correspondingly. See the green arrow flow. Note that the green arrow flow is about passed-in-out object. It starts only from NRS call. It never starts from DCL declare. As another example, the memory box model shows the identified phases and operations for memory addressing, allocation, use, and deallocation box. The operations flow helps in identifying possible chains of box weaknesses. To each BFMax model corresponds one BF cluster. Focus in this talk are the clusters of input-output box, data type box, and memory box. Methodology adjustments are undergoing on cryptography box and random number generation box, and some more are under development. Please visit our BF website to find more details and references to our publications. Each BF class has a strict definition and taxonomy. For example, two of the BF classes that we'll use during the hands-on session, memory addressing box MET and memory use box MAS, have the following definitions. And sets of possible operations where such bugs could happen, causes, the possible improper operations and operands, consequences, improper operands for next weakness and the possible final errors, and attributes with values for the operations and the operands. During the hands-on session, we'll use also the data validation box, DVL, data verification box, DVR, name resolution box, NRS, type conversion box, TCV, and type computation box, TCM BF classes. Note that the BF classes are bug classes. Every class has the bug as a cause, but not all classes would have an improper operand as a cause. So we are classifying weaknesses, but the classes themselves get established through modeling bugs in the operations. The bugs are the primary focus. The bug in an operation could cause a final error or a chain of weaknesses that ends with a final error and eventually leads to a security failure. The bug is the first cause in the weaknesses failure chain. It is the error in code or the error in specification. It's the error in the first operation that must be fixed. The chain of weaknesses is the security vulnerability. And we're classifying the software bugs that cause chains of software weaknesses to allow precise descriptions of the security vulnerabilities that exploit those weaknesses. Remember, going backwards from the failure, the bugs are under a pile of weaknesses that must be understood to clearly specify the bug. Like in the bad log chain, a bug in input verification is the cause for a DVR weakness that leads to a TCM weakness, that leads to a MAL weakness, that leads to a MET weakness, that leads to a MAS weakness that causes buffer overflow. To share some history, the first BF class, buffer overflow, BOF, was introduced in my Towards a Periodic Table of Bugs talk in 2015, which followed our publication on CWE problems and some early attempts to formalize CWEs and CVEs. The taxonomy of BOF is now covered by the BF Memory Use Bugs class, MAS, which is part of the BF Memory Bugs cluster. The BF classes are being validated towards CWE. We identify the CWEs related to particular BF classes via filtering their descriptions by specific keywords, automated extraction of CWE clusters by parent-child relationships, and iterative rounds of manual CW reviews. For example, we have identified 161 input-output related CWEs, 78 data type related CWEs, and 52 memory corruption related CWEs. We generate digraphs of CWEs that show their correspondence to the BF classes by operation or by consequence. For example, the data type box diagram by operation shows that most of the data type related CWEs are about weaknesses that occur at decoration and definition. This combined 50% are covered by the BF decorations box class DCL. The next two large clusters are about data type related calculations or evaluations. This combined 33.3% are covered by the BF type computation box class TCM. The list represented are the name resolution, NRS, and the type conversion, TCV weaknesses. As another example, the input-output box diagram by consequence shows that 68% of the input-output CWEs relate to injection final errors, query injection, comment injection, source code injection, perimeter injection, and file injection. There are several CWEs with wrong data consequence, but also quite a few with no consequence listed at all, or difficult to determine. With these digraphs, we show that each BF class covers all related CWEs and potentially beyond, while, as demonstrated by examples, providing a better structured way for describing vulnerabilities.